Greetings of the day. I am Dr. G. Sreenivasulu, Assistant Professor, Department of CSE. I completed my PhD in Bharatiya University in the year of 2023. I am currently working in the Department of CSE, and also I am working as a IQSE co-coordinator. I am presenting today. The topic is compiler design, code optimization techniques in compiler design. This is the flow of the presentation. First comes under introduction, types of code optimization, principal sources of code optimization, its types, loop optimization and its types, peephole optimization, its types, and some reference books I kept. This is the flow I am going to cover today. This is very important topic in regarding of compiler. You all know what is compiler. Compiler will translate one type of language to another type of language. That is, one higher type of language to lower type of language. That is called machine understandable language. Human understanding language to machine understanding language. For that we have to use compiler. In that compiler design, we have one topic called code optimization. It is very important topic regarding what you call in the whole phase of compiler. Next, coming to introduction. What is code optimization? It is the process of reducing the number of instructions without changing the outcome of the program. Here one point to remember: if you reduce the number of instructions, but outcome should not be changed. That is the main what you call core point here. There are two types of what you call code optimization techniques are there. One is mission independent code optimization. Second one is mission independent code optimization. One is mission dependent. One is mission independent. What is mission dependent code optimization? Any optimization techniques based on mission. That means any system or computer, that is called mission dependent code optimization. And what is second type? Mission independent code optimization. Mission independent code optimization in the sense it is not related to mission, it is related to user. If any optimization techniques can be done by the user, that comes under the mission independent code optimization. Before going to the types of mission dependent, mission independent, we have to, what is the use to optimize the code? What is the reason to optimize the code? Why we have to optimize the code? Because to improve the performance and efficiency of the code, we have to go for what you call this code optimization. To improve the performance and efficiency. Here performance and efficiency in the sense of time and space. What is time complexity here? How much time what you call to require to execute a particular source of code or particular instruction based on the time and space. Space means how much space or how much memory required for the what you call this computer to store the particular source program. Based on this time and space only, this what you call performance and efficiency of this what you call compiler will estimate. That's why we call it as this is the main optimization, main phase of the compiler. We call it as a main phase of the compiler. It will comes under the sixth phase of the compiler, code optimization. It will take optimized code as an input. It will produce what you call executable code as an output. Next. There are different types of code optimization techniques are there. One is principal sources of code optimization. Next one is loop optimization. Next one is basic blocks optimization. These are the three types to optimize the code in compiler design. Again, in principal sources of code optimization, there are different types. And again, in loop optimization also, there are different types. And again, in basic blocks optimization also, there are different types. This overall concept is to optimize the code to improve the efficiency of the compiler. Efficiency in the sense in the form of time and space. Here comes under the principal sources of code optimization. It is the basic type of compiler code optimization compiler design. Here comes under the 5 different types of code optimization techniques are available in principal sources of code optimization. One is common sub-expression elimination. Next one is compile time evaluation. Next one is what you call code movement or code motion. Next one is dead code elimination. Next one is strength reduction. These are the 5 techniques involved in the principal sources of code optimization. We will go for one by one. First one is common sub-expression elimination. In the name only itself, we can find the answer. What you call common sub-expression elimination. Common sub-expression is nothing but there are more than one expression is there in the code without using the multiple times. For that, why we have to waste the time and space to of the compiler. For that, we are removing the common sub-expression elimination. We will use this extra instruction output to the previous what you call expression output. Here, if you see example, before elimination and after elimination, if you see example, b equal to a plus 1 into 2, b equal to a plus 1 into, I'll highlight here, b equal to a plus 1 into 2, b equal to a plus 1 into 2, 1 second, b equal to a plus 1 into 2, b equal to a plus 1 into 2, and next one is c equal to a plus 1 into 2. They both expressions are same only, but we are using 2 times in the code. To remove that, we this what you call concept, we have to use common sub-expression elimination without what you call without changing the output of the program. As I clearly mentioned, without what you call before sub-expression elimination or after sub-expression elimination, with example, if you see there, the what you call size of the code will automatically reduce, and the time to execute the each instruction also will be reduced. Next, go to compile time evaluation. Next optimization technique is compile time evaluation. This is the what you call technique can be done in the compile time instead of runtime. Here also again it will be classified into 2 types. One is constant folding. Next one is variable propagation. Variable propagation or what you call copy propagation. Variable propagation or constant propagation. They both are the same names only, but they will call it in a different way. Variable propagation, copy propagation, and or constant propagation. First one, you go for constant folding. Here, they evaluate the expression and submit the result. Before going to the what you call to submit the value in the what you call this code, we have to evaluate the constant value and submit the in the what you call in program or code. It will automatically reduce the compile time. Why? Because instead of executing 22/7, I can put 3.14. Why? Because compiler will take less time to execute 3.14 instead of 22/7. Why? Because 22/7 include the division operator and also two constants, 22 and by 7. Instead of that, compiler will take less time to execute 3.14. Why? Because it is a single constant. That is one of the what you call compile time code optimization technique. We will substitute the constant value instead of the expression. That is one type of compile time evaluation. Next one is variable propagation or copy propagation or constant propagation. These all same names only, but they will call different way. Here constant will be replaced by variable. If we execute variable in compiler design or what you call we got as in source code, it will take more time than the constant or value. Because of that, we are replacing the variable by the value. That is the example I mentioned here. Area equal to pi r square. I am mentioning the what is the pi value 3.5. We know the pi value, but instead of putting pi variable, I am putting 3.14. Why? Because compiler will take to execute 3.14 less time than pi. Why? Because pi, it will go for the pi what you call where it will be value will be stored, then it will be replaced by the pi, then it will be executed. Instead of that, I am keeping pi equal to 3.14. Then I am reducing the compiler time. This is the one of the technique can be done at the compiler time in code optimization techniques in compiler design. Next one is code movement and or code motion. The code movement or code motion are both names, but they will call it in a different manner. Here it is a technique. Which moves the code outside of the loop. If it won't have any difference, it will be executed in the inside or outside loop. That means if any expression or any any instruction will be there in the inside the loop, we are moving the outside the loop. Why? Because it is nowhere related to the loop variable. Why? Because if loop variable related only, that expression what value will be changed. Instead of putting that expression in the inside the loop, I am moving the outside the loop. Why? Because to reduce the compiler time. Here I mentioned the this example without optimizing the code. After optimizing the code, if you see x equal to y plus z, it is nowhere related to loop variable. Instead of that also I am keeping the inside the loop. If you take n is equal to 100, this x equal to y plus z will execute 100 times. There is no use 100 times without using. Instead of that, if you keep this x equal to y plus z outside the loop, it will execute only one time. Because of that, this compiler time automatically will reduce. That is the one of the most important optimization technique in principal sources of code optimization. That is called code movement or code motion. Here we are moving the code from inside the loop to outside the loop without changing the the outcome of the this code program. Next one is dead code elimination. Here it includes the eliminating the statements or instructions that are never used in the whole program. Without using the program also, we will mention some instructions in the code. What is the use? That's why to optimize the this compile time or this space, we are removing the dead code, that is but not executable code. Here I mentioned the example I equal to 0 if I equal to 1 and some statements a equal to x plus I. If I take an I equal to 0, what is the use to check the condition if I equal to 1? It won't execute at all in the whole program. That's why I'm moving I'm replacing this code from the this executable program. Then only it will automatically reduce the compile time and also this space to store the program. That is also one of the elimination technique or code optimization technique in principal sources of code optimization. Dead code elimination in the sense we are moving the not executable code from the program to outside. That's all. Next, last one is strength reduction. Here, strength reduction also, it is one of the code optimization technique used to replace the expensive operator by cheaper operator. Here, based on the operators only, there are different operators is having different compilation time. Based on the compile time, this strong operation or weaker operation will be decided. Here, I am replacing the expensive operation by cheaper operator to reduce the to reduce the compile time. That we call it as a strength reduction. Here, if you see example, a equal to 2, b equal to a into 2. Actually, instead of putting that multiplication operator, I am using plus operator. Instead of putting star operator, I'm replacing plus operator. Why? Because star operator will take more time to execute by the compiler instead of plus operator. That's why here if you see a equal to 2, b equal to a into 2, what is the output? 4 only. And b equal to a plus 2 also 4 only. What is the use to use costly operator or expensive operator than cheaper operator? Why? Because it will automatically reduce the compilation time. This is also one of the technique in compiler design to reduce the compile time. Next topic, next code optimization technique is loop optimization. It is also one of the important technique in code optimization. Why? Because most of the compiler time will be taken in the inside the loop. To optimize the loop, code in the inside the loop, it will automatically reduce the this space and time of the this program, execution of the program. That's what I mentioned here. Much of the compiler time is spent inside the inner loops. The running time can be minimized if the number of instructions inside the loop can be minimized or moving the outside the loop. The loop optimization is also comes under mission independent optimization. This all Principal sources of code optimization are loop optimization, and this basic blocks optimization comes under the mission independent what you call code optimization techniques only. There are different types, but this concept is same only. We have to optimize the code or optimize the compile time, optimize the space. Here again loop optimization also come what you call, there are several types. 5 types are there: loop invariant computations, loop unrolling, loop fusion, code movement or code motion, strength reduction or reduction in strength. Next we'll see one by one. First one is loop invariant computations. Here in loop environment, any statements loop which results the computations do not change over the iterations. That's what here. It is also same like as code movement. Loop invariant computations also same as code motion or code movement in principal sources of optimization. If you take this example, for I equal to 0, I less than 5, I plus plus. Here the loop variable is I. Inside the computation are expressions related to C equal to A plus B, D equal to A minus B, and E equal to A star B. These 3 expressions nowhere related to loop variable. Why? Because a loop variable is I. If you increase the loop number of times, it will automatically increase the compilation time without changing the values of C, D, E. That's why I want to move the C equal to A plus B, D equal to A minus B, E equal to A star B into outside the loop to reduce the compile time. If you move outside also, there is no change in the result of the program. That's why I am moving the outside the loop. It is also same like as code movement or code motion. Why? Because here we are moving the code from the inside the loop to outside the loop without changing the output of the program. Next is loop unrolling or loop fusion. It is also one of the technique in loop optimization to optimize the code. Loop overhead can be reduced by reducing the number of iterations. It is the vertical concept of loop fusion or loop unrolling, replacing the body of the loop. Here if you see example, you can understand clearly. I equal to 0, I less than 100, I plus plus. What is the inside the loop? Add function will be there. Instead of that, I am reducing the I equal to 0, I less than 50, I plus plus. I'm adding the extra add function inside the loop. If you see without optimizing code or unoptimized code, loop variable will be executed 100 times. Here after optimizing, loop variable will be executed only 50 times. Automatically half of the time will be reduced in the inside the loop. To do some what you call optimization techniques in the inside the loop, it is the concept of loop unrolling. Loop unrolling means to reduce the loop overhead. To reduce the loop overhead, it will automatically reduce the compile time. Next is loop fusion or loop merging. Here I am what you call I want to merge. I want to reduce the compilation time inside the loop. Loop merging means adjacent loops can be merged without changing the output of the program. If you see example, for I equal to 0, I less than 10, I plus plus, a of I equal to a of I plus 10. The same loop I am using again. Instead of using 2 loops in a single program, I am using single loop and 2 expressions inside that particular loop. Then it will automatically reduce the what you call compile time or execution time of the program. That is also one of the technique to optimize the code or to optimize the compile time in loop optimization. Next one is code movement or code motion. This already I discussed in principal sources of code optimization. Why? Because the same. If you do code movement in what you call inside the loop, it comes under loop optimization. If you do code movement some what you call basic blocks of the program, that will comes under the principal sources of code optimization. Here also I mentioned the same example. If you refer that one, this is also same only. Next one is strength reduction. Strength reduction also I mentioned here there principal sources of code optimization. Why? Because it is also same. If you do strength reduction inside the loop, it comes under this loop optimization. If you do outside the loop this strength reduction concept in outside the loop, it will comes under the principal sources of optimization. Here same only. If you replace the expensive operation by cheaper operator, it will reduce the compilation time without changing the output of the program. This is also one of the technique in loop optimization to optimize the code. And last one is peephole optimization, or we call it as a basic blocks optimization. Here it is also one of the effective technique for improving the target code in peephole optimization. These techniques apply to improve the performance of the program by examining the short sequence of what you call instructions. Peephole is a movable window. Some block, we call it as a some block. The alternative name of this peephole is window optimization only. Here window means some set of statements or instructions in the source program to optimize that particular block or set of instructions that comes under the peephole optimization. The peephole is a small moving window on the target program. The code in the peephole need not be continuous. That is one of the important points should be remember. In peephole optimization, code should not be continuous. That is one point to remember. Next, there are different types of peephole optimizations. Here I mentioned 5 peephole optimization techniques. Redundant instructions elimination. Next one, removal of unreachable code. Flow of control optimizations. Algebraic simplifications. Next, use of mission idioms. These are the 5 techniques comes under peephole optimization. I already told what is meant by peephole. Peephole is a small window, a small block in the source code. First, coming to first what you call this optimization technique. First one is instructions elimination. If you see this example, 2 instructions are there. Move R0, A. Next, move A, R0. Move A, R0. If you remove the what you call the instruction 2, what you call why, because already instruction 1 the output of the 2 instructions are same. Why? Because move R0, A means the A variable will move to the R0 register. Next, A, R0 also same only. Move A, R0 also same only. Why? Because A variable value will be stored in the R0. Instead of putting 2 instructions, I will use only 1 instructions for multiple times. That is also one of the technique to optimize the code or compile time by using instructions elimination. That is will be repeated. It is same as common subexpression elimination. Next one is removal of unreachable code, that I already told. Removal of unreachable code also same as dead code elimination. If any code not reachable to execute the program, that is called comes under the removal of unreachable code or not reachable code. If you see example, same example I mentioned, I equal to 0, if I equal to 1, sum equal to 0. If I mentioned I equal to 0, what is the use to check if condition I equal to 1? It won't check at all in the complete entire program. That's why we will remove the unreachable code, or we call it as a unreachable code, we call it as a dead code elimination. Next one is third one is flow of control optimizations. This is also one of the technique in peephole optimization to optimize the maximum time of compiler. Why? Because here they are using the concepts called jumps. Without using the jumps, without changing the results, I will reduce the number of jumps of the compiler. Using peephole optimization, unnecessary jumps can be eliminated. That's what. To move the compiler from one label to some other label, it will take more time. To remove that, I am using this flow of control optimization technique to remove the unnecessary jumps. First one is go to, if you see example you can understand, go to L1, next go to L2, next go to L3. Instead of going L1, L2, L3, I will go direct to L3. Why to go for L2 and L3 or L1 and L2? Instead of going L1 and L2, I will go to direct L3. There is no change in the output of the program. If you go direct to L3 or if you go L1 and L2, L3. There is no change in output. That's why I'm using this optimized code to go to directory L3. That is called go to L3. This is called multiple gems can be removed by using the flow of control optimization. Why? Because in gems only, if you move the compiler from one label to one place to another place, it will take more time. This is one of the important concept in peephole optimization to reduce the compile time in this code optimization technique. Next one is algebraic simplification. This is also one of the technique, code optimization technique in people, comes under the people optimization. Here there is no n amount of algebraic simplification that can be attempted through people optimization. Here it is also like as if you do some modifications of the some expression, the result of the expression it won't change, but we are doing some extra modification. What is the use? To remove that what you call extra time or extra space, we will use this concept is called algebraic simplifications. X equal to x plus 0 or x equal to x into 1, x star 1. If you do x variable to add 0 also same only. If you do x equal to x star 1 also same only. Instead of doing this what you call extra operations or extra instructions, I will use direct x value in the code. It will automatically reduce the number of instructions in the number of instructions or number of compilation time also it will be reduced. This is also one of the optimization techniques, comes under the peephole optimization. Next, last one comes under use of machine idioms. This is also one of the technique in peephole optimization. Here I am using the CPU instructions directly instead of using the what you call normal code instructions. Why? Because compiler will take to execute the CPU instructions will take less time than when compared to what normal instructions. That's why I'm using the machine idioms. If you see example, you can understand. This is the process using the powerful features of CPU instructions. I equal to I plus 1. That is called what you call I'm increasing the I value by 1. Instead of doing that, I can use directly INCI. It will automatically increase the value of I by I plus 1. That is the machine idioms or machine instructions. This is predefined by the microprocessor. If you use microprocessor instruction, the compile time or what you call this space of the program will automatically reduce. This comes under the overall. We will go for the overview of this code optimization techniques. It is one of the important phase in compiler design. Here there are different types of code optimization techniques are there. What you call this loop optimization, peephole optimization, principal sources of optimization. These three concepts this core point is same only, to optimize the code to improve the performance of the performance and efficiency of the compiler. Performance and efficiency in the sense in the form of what you call this space and time. If you do, you can do what is the there are different ways. I already mentioned with examples. If you refer that one, it will be automatically reduce the compile time and also space. It will automatically improve the what you call this performance of the compiler. Thank you. And these are the references I am using what you call to represent this what you call this concept. This my main book is what you call J.D. Ullman. J.D. Ullman is the basic textbook in the what you call in compiler design. I am referring that one, and also some online material. I am preparing this PPT. If any doubts, you can ask in what you call this comment section. I will be what you call I will answer as soon as possible. Thank you.